Hello, everyone. Can you guys hear me? Great. You may notice that I've changed the background. So I've decided that given it's very boring to sit at home to do lectures and for you guys to learn from home, I may well just give you a world tour at every lecture. So I'll try to use a different background from today's lecture onwards. So this one, we are waiting for more people to show up. So this one is a background from Singapore. Okay, so anyone have had a durian before? Yeah, so this is one of the most popular durian hawker in Singapore called Air Force durian. They sell durian in one of the their shops. It's a seasonal item, so every year there are 3-4 times offering of the durian. It's a fruit that's very buttery and very flavorful. Someone even go all the way to say durians are stinky. So if you haven't tried it before, like I recommend you to try it. You may like it, you may not, but if you miss the chance of trying it out, there's a small chance that you'll regret it forever. Because I personally love durian, and I would I would pay like $100 to have the authentic Maosan King durian shipped directly from Singapore, or like spend a day retreat to the tropical area, either Singapore or Malaysia, to just to have durian. All right. Looks like we've got everyone. So let's get the lecture started. So today is our 13th lecture. We're gonna be officially moving into the second half of the course on online learning, okay, or online convex optimization. So today is going to be an introductory lecture on online learning, where I'm gonna make sure that you guys start to appreciate the problem. We're going to be setting up the problem. We'll give a very concrete example on learning from expert advice, and then we'll analyze the different algorithms for learning from expert advice, and measure their performance in terms of mistake bounds and so-called regrets. All right. So before I start, let's have a quick recap of what we've learned so far. Okay, so far we've learned algorithms for convex optimization. Okay, so there are a whole bunch of algorithms that we've learned. So we learned the gradient descent or subgradient methods. So when we have access to first order article of either the gradient or subgradient, we learned Prox gradient. We learned, I guess, a stochastic gradient method. So maybe it's a projected version of the stochastic gradient method. And then in the last 2 lectures, we've learned Newton's method and IPM. And so IPM is an interior point method. In particular, we went over with details on how the barrier method works. But there's also the primal dual interior point method that's very similar to barrier method, but it doesn't require an inner loop of Newton's method. Okay, so in terms of problems that these methods can solve, so suppose all we want to solve is a convex optimization, unconstrained convex optimization problem. Then we know that without any additional assumption, say we can minimize a potentially non-smooth objective function, then the gradient methods is only gonna give us a rate of 1/epsilon squared. So this is measured in the number of iterations it takes to converge to an epsilon suboptimal solution. Prox gradient in this case isn't any different. So this is essentially like trying to this is essentially trying to solve I guess a proximal minimization problem. And suppose you smooth it. Suppose you add smoothness to it. Then you end up getting like 1 over one. You end up getting 1 over epsilon. Okay. And suppose we add a strong convexity. Suppose we add m strong convexity, then the gradient method suddenly becomes L over m, where L is the smoothness parameter and m is a strong convexity parameter, and the iteration complexity becomes logarithmic in 1 over epsilon, which is an exponential improvement. In addition, suppose we add acceleration, then we can accelerate the smooth problems into 1 over square root of epsilon, which is a lot faster. And we can with acceleration, the strongly convex problem becomes square root of L over m log 1 over epsilon. Okay, which means that you only need a square root number of iterations in the condition number before you can reduce a constant factor of the suboptimality. Okay, so prox gradient is essentially the same as gradient descent. Stochastic gradient descent, on the other hand, like have more or less the same complexity for the convex and possibly non-smooth problem, and adding smoothness doesn't really help. This is due to the fact that SGD needs to take a diminishing step sizes in order to guarantee convergence. When we assume strong convexity, like we didn't prove this, but we've stated its result. When we assume strong convexity, we can actually improve the stochastic gradient methods to 1 over m epsilon. So this is even true, even if smoothness even if we do not have smoothness. Okay. On the other hand, so this summarizes the first order optimization. For the second order optimization, we talk about Newton's method. So Newton's method, the first thing that we say about Newton's method is that it has to satisfy the twice differentiability, right? So that rules out the only convex function. Like we can't deal with it using Newton's method because even the gradient doesn't even the gradient might not exist. And with just the smoothness, we are also cannot directly apply Newton's method because smoothness doesn't require the Hessian to exist. It only requires the second order weak derivative to exist, which means that for some points we cannot actually evaluate the Hessian. Okay, which means that adding strong convexity also doesn't help. But suppose we, in addition, add the fact that the Hessian satisfy the Hessian-Lipschitz, this is even higher order smoothness condition, then we can start to analyze the Newton's method. And we've seen that the Newton's methods have two phases. In the first phase, it takes a fixed number of iterations for us to get to K0 is parameterized by M, L, and the capital M. So this is capital M, Hessian-Lipschitz condition, and also it depends on the parameter of also backtracking line search alpha and beta. Okay, in the second phase, the Newton's method converges quadratically with log 1 over epsilon, but with a constant in front of it that depends on M, L, M, alpha, beta. Okay. So this analysis doesn't reveal the advantage of Newton's method that much, even though we get in terms of condition number, even though we do get local quadratic convergence. If you assume self-concordance, then you can replace this with K0, which depends only on alpha, beta, and plus the universal constant log 1 over epsilon under self-concordance condition. Okay, you can I guess add constraints. Suppose you have a constraint optimization problem, as we the general framework of convex optimization that we formulated. Suppose you have constraints. If you only have affine constraints, the Newton's method can be used to solve that through the KKT condition, and you can calculate the update direction by solving a slightly larger linear system of equation using and then use Newton's update to simulate that KKT condition. Okay, so suppose with affine constraint, then you get exactly the same rates as the unconstrained version. So that problem is solved when we talk about interior point methods, where the constraints are dealt with using something called a barrier function. Okay. In particular, we talk about the log barrier function, which is a general family of barrier function that satisfy the condition that it is self-concordant for say linear inequality constraints and quadratic inequality constraint and many more. Okay, so suppose you have self-concordant constraint, you can analyze the interior point methods, which essentially traces the so-called central path. Okay, by increasing the parameter t, which add to the artificial part of the objective that's coming from a barrier function and use it to replace the actual constraint, so that we're reducing the problem into an iterative solving of Newton's method. And with that, we know that in the outer iteration, so under the self-concordance condition, the interior point method satisfies that it converges linearly. Okay, and suppose it's self-concordant, then this convergence doesn't really like the number of Newton steps. It's also on the order of log 1 over epsilon. Okay, and thanks to the property of self-concordance that doesn't depend on the condition number m and l, and this is really like a very powerful approach that can solve a general family of convex optimization problems with arbitrary set of constraints. And the dependence on the number of constraints is only logarithmic in the number of constraints. So it same. Okay, so this summarizes everything that we've learned so far, but there are like several missing boxes. Assuming the function being Hessian-Lipschitz or satisfying some kind of high order smoothness, does these conditions help gradient methods or stochastic gradient methods? So in general, no, but there might be specific cases you can use. It's established that the higher order smoothness can actually have gradient methods or first order style methods. Okay, so in general, not useful. Okay. Oh, with constraint is really not applicable. On the other hand, suppose we have interior point methods, then often we can reformulate non-smooth convex optimization problems by adding dummy variables, by introducing dummy variables so that we can replace some part of the objective with constraints. Then it suddenly becomes solvable using interior point methods. Okay, wait for new late. All right, so so that summarizes the lectures that we had so far, and most of these should sound familiar to you. Okay, so let's start a new chapter. So today's lecture and actually for the remainder of the course, we're going to be focusing on a generalized setting of convex optimization problems called online learning or online convex optimization. So online learning is slightly more general because it covers things that are not convex. But as we'll see later, the techniques of doing online learning mostly focuses on convex first order methods. Okay, so before talking about online learning, so I wanted to remind people about the setting of statistical learning. Okay? So this is a typical setting that people use to analyze machine learning. So in machine learning, we assume that there are data sets that are drawn IID. So think about supervised learning, or more easily the classification problem. Think about spam filtering. When you receive an email and you have a feature vector that describes that email, and you wanted to learn a spam filter that automatically classifies these emails into spam or non-spam. Okay, so the settings are the following. You have data sets x1, y1, x n, yn, that's sampled IID from some distribution D, from some unknown distribution D. Okay, in the simplest version of the problem, let's say that x is in a space x, so you can think about this x to be, well, r to the d, or 0, 1 to the d. Okay, so this is a set of feature vectors, and let's say that y is binary. It's either 0 or 1. Okay, spam or non-spam. And in this setting, the learner is often given the so-called hypothesis class. And let's simplify the problem further. So let's assume that the problem is so-called realizable. So realizable says that there exists an H star in the hypothesis that's consistent with all the data, which says that there exists such a A star which produces a label. Okay, the probability under x, y drawn from this D, H star of x is equal to y. Is equal to 1, right? So with probability 1, then the observed data point is consistent with H star of x. Meaning that there exists a classifier in the family of classifiers that give you 0 error. Okay, so the goal of learning is to find H in the hypothesis class such that such that we get as lowest we get an error that's as low as possible. So the error under this distribution D is equal to the expectation of the mistake. So recall that this is the true label with probability 1. So this is essentially the error, the expected error of always playing this hypothesis H. Okay. And the goal of learning is to show that under the realizable setting is to show that this goes to 0 as the number of data point goes to infinity. Okay. So this is called statistical learning or batch learning, or sometimes in some settings it's also called probable approximate correct PAC learning. So this is Valiant, Vapnik, and so on. And a lot of the pioneers of machine learning have studied the problems on. Okay. Just 1 second. Let me turn off the computer of my wife. All right, I'm back. So online learning uses a slightly different set of assumptions, and in some sense, it's more general. Okay, so online. In online learning, you observe one data point at a time. So notice that in batch learning, the data set is all available to you before you can make the decision of learning and how you make use of the data set to find such an age. In online learning, on the other hand, you have to do it online. You have to do it on the fly. So here's the idea. So at time 1, so all you have access to is this x1. Okay, so you have to choose h1 from the hypothesis class using only h1, and then make predictions. Y1 hat is equal to h1 x1. Okay, and after you make the prediction, then the true label y is reviewed, and then you suffer a loss if your prediction is incorrect. Okay, so in the second step, the data that's available to you is a data point x1, y1, and also x2 that's available to you. And at time ht, what's available to you is x1, y1 to xt minus 1, yt minus 1, together with xt. Okay, and each time you predict ht, xt, and then review the true answer, which is yt. Okay. So one key to notice is that in this setting, we're not really making any assumptions about how the data is generated. Okay, so the data can be arbitrary or adversarially chosen. So there can be an adversary who chooses this sequence of examples carefully to beat your learner, so that your learner won't be able to construct a hypothesis that works well here. Okay, so not necessarily IID. Then how do we measure the performance of this, since we do not have a distribution of the data, and then this expectation is not really defined? Okay, so the objective measure for online learning is a so-called mistake bound. Okay, so let's say the mistake bound M. So if an algorithm A satisfy that A makes smaller than M mistakes for all sequences of observation x1 h star x1 x star xt and so on. When t goes to infinity, for any such sequence that can be an infinite sequence, then we say that algorithm A has a mistake bound of M. Okay. So sometimes when we get to xt and h and yt, and this M can be parameterized by t. But in this lecture, so we want to find a regret bound that's a constant, and it doesn't go to infinity even as the sequences get to infinity. Okay, I hope the setting is clear. I hope the setting of online learning in this simplest setting is clear to people. So I wanted to say that starting from today's lecture, so we'll have more board work, so more like writing on the board. and much fewer number of slides that I'm able to show. So it is critical that you guys can appreciate the setting and can appreciate the arguments that I make in every line. So if there are any arguments that's unclear, so I haven't really started to make any arguments yet. I'm only setting up the problem. But during the analysis, and I'm going to try explaining every detail about an inequality. But if any part that is not clear, please unmute yourself and ask. Or if you are not comfortable doing that, just type in the Zoom group chat, and then I'll make sure that I respond to you. Because it's important that you guys are following the arguments. And if you have a question, if you have some concerns about how is it possible that we have this inequality, then somebody else in who's your peer may also have the same question. So it's a good idea to clarify that right away. Okay, so for now, like we've talked about the setting of online learning, which you have to make a sequence of online decisions and learn H1, H2, HT based on the information set that's available to you. And then we're going to be evaluating any algorithms that generates these sequences of H1 to HT using the number of mistakes that this algorithm makes, the cumulative number of mistakes this algorithm makes. Okay. So let's talk about the first algorithm. So that's like the trivial algorithm for this problem. It's called algorithm A, consistency. This is also known as follow the leader, or empirical risk minimization, ERM. Empirical risk is an empirical error, so we want to find the one hypothesis that's consistent with everything that we've seen so far. So that hence the term consistent. So here's how this algorithm works. So you start with defining a set V1 to be just equal to the hypothesis before we start anything. And then for T to be 1, 2, 3, and going onwards. And this learner, this algorithm will receive XT, okay? And pick any H in this version of the hypothesis class, V1, okay? This is also sometimes referred to as version spaces. So this V1 is a version space number 1. And then predict YT hat is equal to, this is VT, H of XT. Then receives the feedback of YT. So this is the true label, which we know by the realizability assumption that there exists as one H star within the hypothesis class that gives us this. Okay, and then once we have this, a critical step is to update the version space is equal to the set of all H in this current version space, but in addition, it satisfies for this new data point that HXT is equal to YT. Okay, so notice that with this update, this is essentially saying that for any H in VT plus 1, H star of Xi is equal to H of Xi for all I from 1 to T. Okay, that's why it's consistent. So notice that this algorithm is a simple elimination algorithm that basically looks at what happened until this point, and then get rid of all the hypotheses that's inconsistent with the evidence that you objectively observe. Making sense, right? So this is the simplest possible algorithm that we can think about. So what is a mistake bound that we can derive for this algorithm? Okay, so notice that for each mistake, we can eliminate at least one hypothesis. This is a hypothesis that we pick, right? So we can maybe with this update rule, we can eliminate more than one, but we know that we can eliminate at least one. Which says that, which gives us a trivial upper bound of M, that the M of this, what's this? Satisfy that this is smaller than the cardinality of this hypothesis class -1. Okay, so if the sequence goes on and on and on, so at most I can make this many mistakes, because after I eliminate H cardinality -1 mistakes, then all is left must be H star. Okay. So this is trivial, and it doesn't really say anything about us learning meaningful things, because the hypothesis class is often exponentially large. But it turns out that this is also like a lower bound for this algorithm. So thanks to this example. So let's say that we can define the X space to be, say, 1, 2, to H cardinality. So this is a discrete space on integers. And let us now define the hypothesis class. So we have hypothesis class being H1, H2, H cardinality. That's indexed by this. And each HI makes a prediction be 0 if I guess X is smaller than or equal to I, and Y and 1 are the Y's. Okay, so HI is in some sense a step function that outputs 0 whenever the input X is smaller than the index of this H itself, and 1 otherwise. Okay, so now let's say that the adversary decides that the learner is going to receive a sequence of input, x1 is equal to 1, x2 is equal to 2, to all the way to h is equal to H cardinality. Okay, and the associated label Y is equal to Y1 is equal to 1, Y2 is Y1 is equal to 0, Y2 is equal to 0, and I is equal to 0 until the very last, where YH is equal to 1. Okay, so notice that suppose we okay, so maybe let's make this a strict inequality. Okay, so it's a step function with continuity on the right hand side. So so at the beginning, when we do not have anything, then any classifier is consistent. So we can pick, the algorithm can pick H equal to H1, and then it makes a mistake. At time 2, H2 is consistent, then another mistake. At time 3, H3 is consistent, then another mistake. Towards the very end, it's only until the last data point when the learner finally figure out that H star is actually equal to H cardinality. So that does this make sense? Right. So based on this construction, so the learner, while satisfying the rules of picking any H that is consistent with the entire data set, since it just happens to be that within the set of ambiguities, the learner is always going to be making a mistake. each time like the learner decides to break symmetry in this way, which leads to one mistake at every single time, which says that the regret bound, upper bound, the trivial regret upper bound that's proportional to the cardinality of the hypothesis space is actually tight. Are there any questions about this upper and lower bounds? Okay, so looks like we're okay here. But this is really bad. Let's maybe try to patch this consistency algorithm so that we get something that's not that's not so trivial. Okay, so algorithm B called halving. Okay, so here's how this algorithm works. So again, we start with a version space V to be just H, and we wanted to, based on the observation, to eliminate the remaining hypothesis within the hypothesis class. So for T from 1 to 3, so receive xt. So far, everything is the same as what we had before in consistency. This is just to follow the rules and then learn, then predict yt hat is equal to h with input xt, and receive the true label, and then the difference is here. So we now want to yeah, sorry. So when we do the prediction, instead of predicting using right, instead of predicting using an arbitrary h, okay. So now let's use the majority voting of all the remaining hypotheses. So vote of all the h in the remaining hypothesis of h of xt. Okay, if we write it in the formula, so this is arg max of picking, I guess, the output to be either 0 or 1. Then we want to maximize the cardinality of the set of h in Vt such that htx h of xt is equal to r. Okay, we want to pick either 0 or 1 that maximizes the number of hypotheses in the remaining version space that's agreeing with. Okay, and then we receive this. Then we update it using the same formula by keeping everything consistent. Okay, so this is only part where it is different. Okay, so now let's analyze it. So first of all, let's state the result. The theorem. So we have a mistake bound that satisfies that it is only logarithmic in the size of the hypothesis space. Why is that the case? So notice that in every iteration, due to the majority voting rule, for each mistake, at least Vt cardinality over 2 hypotheses are removed. Okay, just take a couple of seconds to think about this. Can anyone point out why? Why is that the case? Why are we able to eliminate at least half of the Vt whenever a mistake is made?
So I think when the mistakes are made, and then that means the vote is incorrect, right? So there's like at least half of the is you made the mistake and it's not consistent with the true label, so we can eliminate them.
Excellent. Okay, so so let's say m is the number of mistakes that this halving algorithm have made, and then after t plus 1 iterations, if m mistake was made, then using this argument, we know that this is smaller than the cardinality of h 2 to the power of minus m. Right? So m is the number of mistakes made so far, and h is the initial size of the hypothesis space. So we are guaranteed to eliminate at least half with every mistake made. Now we know that at the end of the day, like even if t goes to infinity, we still would have h star inside the version space that's consistent with everything. That's why we also have a lower bound of this vt plus 1. A trivial lower bound of 1. So now let's toggle the 2 to the power of minus m to the other side, and then get 2 to the power of m being smaller than h cardinality, and then let's take log on both sides. We get m smaller than log base 2 log cardinality of h. So using the halving algorithm, we improved exponentially over the trivial consistency, even though we're not making any assumptions about how these xt's are generated. It doesn't have to be follow any distribution at all, but we get the learning bound that's more or less the same as what you would expect otherwise in the statistical learning setting. Okay. Another thing to note is that well, is this the best we can do? So notice that like information theoretically, so suppose you observe every single mistake, and then that gives you 1 bit of information about the true hypothesis h star. Like it takes log base 2 log cardinality of h number of bits to even represent, to even uniquely identify where to uniquely index h star within the space of cardinality h cardinality. Okay, which says that this bound is essentially information theoretically optimal. Now, so I personally don't really like this realizability assumption, because it's making something that's very strong, making an assumption very strong about the world. So how can I make sure that my specified hypothesis class will always contain labels that's consistent with the observation? Suppose the label is coming from a random stochastic process where people toss a coin to decide whether it's +1 or whether it's 1 or 0, whether it's head or tail. Then in expectation, nothing can be consistent with this sequences of completely random observation. So the realizability is something that's really strong, and we want to drop it. So what if we drop realizability, and how can we still define the problem appropriately? Okay, so this is so-called like agnostic learning in the statistical learning literature. So in the online learning setting, so instead of bounding the number of mistakes with or rather comparing the number of mistakes your algorithm is making with 0, so let's maybe compete with the best hypothesis within the hypothesis class. Compete versus the best H in the hindsight. Okay, so in which case we can define the so-called regret of an algorithm. So so the regret of this algorithm is a cumulative error that you've seen so far. ht of x not equal to y t. So this is the number of mistakes that your algorithm makes minus the best hypothesis within the hypothesis class that minimizes okay. So in this case, we're not making any assumption about how yt is given. So both xt and yt can be chosen by an adversary. Okay. And in this case, so-called agnostic learning setting, regret is what we are hoping to minimize. Okay, so any algorithms that can do as well as the best hypothesis in the hindsight is what we consider a no regret algorithm. In particular, as t goes to infinity, as the horizon goes to infinity, if the regret is a small o t, that means that on average, the average regret at every time step goes to 0. Okay. Let's maybe like give an example of why this is setting up is of interest. Okay. Stock. Let's consider the problem of learning from expert advice in the agnostic setting with a concrete example of stocks for forecasting. Let's say that there's a stocks that we're trying to predict, say Tesla, and it's either going to go up or go down after every trading day. Okay, so the learner have access to a bag of experts. So for experts to think about who is willing to offer advice, not necessarily who actually is an expert. It has nothing to do with the ability to make predictions. Like think about like stock traders or people who would like to advise you whether to buy or sell a particular stock for their own reason. Okay, so for concreteness, like maybe let's pick a couple of you guys to be this expert. So the expert one, let's say maybe Alex, Alex Rich. So you will be the first expert. So the second expert, I'm looking at my screen on Zoom. So I see Esther. Okay, so this is the second expert. The third expert, that's good. I see Boyuan. So Boyuan was my TA last quarter on CS165A. So Boyuan, so I'll let you be the third expert. And now, like maybe you guys are pitted together with my cat, Raffles. Okay. So Raffles is going to make predictions by jumping either up or jump down. Each morning when he sees me, and if he's jumping up, then his prediction is up. Otherwise, the prediction is down. Okay. So in day one, before day one starts, then Alex predicted that the Tesla stock is going to go down, and Esther predicted that it's going to go up, and Boyan predicted that it's going to go up. Okay, and Raffles say that it's going to go down. Okay, so after the day of trading and all the excitement, the outcome is reviewed, and then the result turns out to be the stock price is went down. Okay. Day two. Okay, so Alex say, oh, I'm gonna revise my my prediction. I think like yesterday I was right, but I think it's gonna go back up. It's gonna rebound. So I'm predicting up, Esther's predicting up as well, and Boyan is predicting down, and Raffles the cat is saying that, well, it's gonna continue to go down. Okay, so as it turns out, after the second day of trading, the result is again down. Okay. On day 3, we have up, down, up, up, and outcome is up. Okay, so the idea about the algorithm that we can use to choose the best expert online without making any assumptions about how this outcome is coming along, like is the so-called like weighted majority. Okay, so this is weighted. So previously, in a realizable case, we had the majority voting algorithm or the halving algorithm. So now, like in the agnostic setting, so the algorithm is called a weighted majority. So instead of taking just the majority vote where everyone has 1 vote, I let every single expert to start with 1 vote, and then slowly discount their credibility if they make a mistake. Okay, so specifically at day 1, before day 1 starts, and all the experts will have a weight of 1, 1, 1, 1. And after day 1, I look at like who has made a wrong prediction, and then discount Esther and Boyuan's credibility by half. So the weights that they have in the next day's prediction is going to be halved. And then Raffles and Alex will remain the strongest sources of opinion that I take. Okay, after day 1 and after day 2, this becomes half because Alex made a mistake, and I guess Esther made another mistake, and Boyuan is right, and Raffles remains strong. And after day 3, we get half, 1/8, yes, 1/2, and 1. Okay. And after every day, my prediction is going to be the weighted majority by looking at the votes and then decide what is the outcome that I'm going to be predicting, and then correspondingly trade myself. Okay. I hope that makes sense. So let's write down the algorithm more formally. So algorithm C, weighted majority. So everything is the same except that we are going to be predicting things differently. So we'll be predict y hat is equal to the indicator of the sum over all experts that I have with their associated weights at this I guess at this time point, this weight at this time point, multiply with their prediction, xt. Notice that this is a binary prediction, so it's either 0 or 1. And if this is larger than half of the total weights at this point, then I'm gonna opt 1. Otherwise, I'm gonna opt 0. Okay, does the formula make sense? So this is the weighted majority. So I'm assigning this a name. Let's call this W to be the total weights. Okay, and this is the weights. The left hand side is a total weights on say up 1. Okay. And after the prediction and the algorithm receive the true label YT, and then discount this WH to H T plus 1 multiply with half for all H that made mistake. Okay, so that's the algorithm, and let's state what this algorithm is gonna be achieving. So this is a weighted majority. We can show that the weighted majority satisfy this m is smaller than a constant 2.4 times m plus log n. So let me parse this for you. So I'm using again m to denote the total number of mistakes that this algorithm weighted majority makes, and m is the number of mistakes of the best expert in the hindsight. And n I'm using it to denote the number of hypotheses or number of experts. Okay, that's the theorem. The proof is actually quite short, so let me finish the proof before we go to the break. Okay, so again, let's think about how this is related to the halving algorithm. So notice that so I claim that for each mistake implies that the total weights drops at least by 25%. Can someone can you all take a moment to think about this and tell me why is this the case? Why would the weights drop at least by 25% after every iteration of after every mistake is made? So think about how you would generalize from the previous analysis of halving algorithm, where every expert have just one vote. So in this case, every expert has vote, but the vote is weighted. So Alex, is that answer to this question or the previous question? Yeah, it's in the right direction. So think about the prediction rule. So think about the prediction rule, and what if you've made a mistake, and what does it say about the total weights? Yeah, there's an answer from Yi saying that at least half of the weights needs to be divided by 2. So that's an excellent answer. So that's really the case. In order for the weighted majority to make a mistake, at least half of the weights needs to be wrong. So if half of the weights needs to be wrong, and then the update will discount those at least half of the weights by half, right? Which gives us a reduction of the total weights by at least 25%. This means that the total weight is I guess, smaller than the initial weight, which is n. Notice that we are assigning a unit weight for every expert at the beginning, n times the 3/4 to the power of a mistake. So you have m mistakes. So I'm bounding the weights after m mistakes by this. Okay, so everyone's following, right? So now like let's also lower bound this this total weight. So the total weight is the total weight of everybody, right? So that includes the weights of the best expert in the hindsight. And no, since we assume that the best we stated that the best expert in the hindsight is a lower has made lowercase m number of mistakes. So his or her weights is only were only discounted up to say half to the power of m, right? So this is because the best expert is part of the pool. Okay, so the best expert's weight is necessarily smaller or equal to than the total weight. So the minimum is smaller than the minimum is smaller than the like, so not minimum. So any one item is smaller than the sum. Okay, and this one is coming from the observation that each mistake will drop the total weight by at least 25%. Now we have a similar equation that we had before. Let's maybe take log on both sides. Okay, so we get m log 1/2 smaller than log n plus capital M log 3/4. Okay, let's notice that this log 3/4 is negative. Let's move this to the other side. So we have m log 4/3 smaller than log n and plus m log 2. Right? Let's divide both sides by log 3/4. So we have m smaller than log 2 m plus log n divided by log 4/3. So I argue that you can bound this constant with roughly 2.4 m plus log of n. Okay, so that completes the analysis for weighted majority. So notice that we do not actually get a regret bound of interest because of this leading factor of 2.4 here. Okay, so this not 1. Since this factor is not 1, so we do not actually get the right regret bound. But suppose m is small, so in the case of realizable setting, m can be set to be 0, then in this case we recover the order of log n by dependence on the size of the hypothesis class. Okay, let's take a break, and in 5 minutes at 2:10 we'll come back and then continue to talk about how we can further improve this and then get rid of this 2.4. Okay, meanwhile, please send questions on the group chat. And I want everybody to appreciate this lecture and to understand how these simple arguments can lead to highly non-trivial like learning bounds. All right, it's 2:11. Let's resume. So far we've analyzed the weighted majority algorithm for online learning from expert advice in a agnostic setting, and we've established that we have a multiplicative style bound on the number of mistakes. In particular, we can bound the number of mistakes that the algorithm makes with 2.4 times the number of mistakes that the expert makes. So in the previous example, this means that you nearly match the performance of the best expert, because the best expert, Raffles the cat, has never really made a mistake at all. Okay, so you lose a little bit in terms of logarithmic factor in the total number of experts, which is acceptable and also information theoretically optimal. But the key question is that how do we really get rid of this 2.4 factor so that we can bound the difference between M and big M and small m using some meaningful bound. Okay, so let's consider two ideas that we may proceed. So the first idea is that, like, maybe discounting the person who have made a mistake by half is too aggressive. Like, maybe instead of discounting by half, let's discount by 1 over epsilon, right? And then we'll choose this epsilon appropriately by optimizing the regret bound over this additional parameter epsilon. So that will lead to an improved bound, hopefully. Okay. So suppose we use 1 minus epsilon. So using the same argument, we know that with every mistake, with every mistake, then the total weight is discounted by at least this much. So we have 1 minus half multiplied instead of with another half. This is 1 minus epsilon. Okay, so this to the power of m, n is the upper bound of the weight. And using the same argument, we know that this weight is smaller than 1 minus epsilon to the small m, because we know small m is the total number of mistakes that's made by the best expert so far. Okay. So notice that we can rewrite this to be n half plus half epsilon to the power of m. So by taking log on both sides, we get m log 1 over 1 minus epsilon smaller than log n plus capital M log half plus half epsilon. Okay, by moving things around to obtain an upper bound on m, so we get m smaller than log n minus log m times log 1 minus epsilon divided by log half plus half epsilon. Okay, minus. And if we move things around, we get log 1 epsilon over log half 1 plus epsilon small m log n log half plus half epsilon. So by choosing epsilon appropriately, we can try minimizing the right-hand side. Okay, so how do we do that? So let's use this simple lemma about logarithmic factors. So for all x that's between 0 and half, we know that log 1 minus x is smaller than minus x. This simply is coming from the fact that this function is concave, minus x, and we make it quadratic, then we can actually sandwich this log function between two polynomials for a reasonable for reasonable x. Okay, so if we then apply like this upper bound here, we can bound the leading term with so notice that this is minus log 1 minus epsilon. So let's add minus on both sides, then we obtain the upper bound of epsilon plus epsilon square divided by over here. Then we need a we need a lower bound, which we can use once. We can use how far away this deviates from 1, and then get half 1 minus epsilon here. Okay, times small m minus some order of log n that we don't really care about. Yeah, the real trouble is no matter how we choose epsilon, no matter how big or small we choose epsilon, this factor of 2 will always be there. So this is a factor of 2, roughly factor of 2, and on the order of 1 plus epsilon. So no matter how small we choose this epsilon to be, it only gonna get us closer to 2 from 2.4 rather than getting us remotely close to 1. Okay, so the first idea doesn't actually gives us gives us the right bound. So what is the trouble? So the issue, like in my opinion, it's really that this algorithm is only in some sense learning from it's only learning from mistakes. This algorithm is only it updates it does not really distinguish two experts on like how good or bad that the expert are, and then discounting the expert like in some sense equally. So like the decision is based on the objective right or wrong, rather than rather than like how far away like this expert is from the decision boundary, right? So for some expert, so maybe this expert's contribution to the weight is tiny. Like maybe this expert's contribution to the weight is tiny, even though this expert would still prefer making a mistake a little bit, then we're discounting that expert by 1 minus epsilon, right? So we want an algorithm that's in some sense sensitive to the extent to which the mistake is made and how much this expert have contributed to the weighted majority vote. Okay, so let's try to smooth it even further using randomization. So the second idea is to randomize the algorithm. Okay, the algorithm is called randomized weighted majority. Okay, so the algorithm works like follows. So we start by set all the weight to be 1 for all h, for all experts, and then at time t, we choose 1 with probability proportional to, we sample from a Bernoulli distribution, and we choose with probability proportional to the weights that prefers this label. If the indicator, if y hat that's coming from h is equal to 1. Okay, and then to make this a probability, let's divide this by the sum of all the weights in this particular location, and 0 otherwise. Okay, so now this is a randomized algorithm, and I'm sampling according to the probability of how these experts would predict. So rather than having a clear-cut plus and minus. Okay, and after that, I'm updating the weights by using our idea 1. So let's discounting those that have made a mistake with one by a factor of 1 minus epsilon for all h that okay. So now let's analyze this algorithm. So again, let's like make let's make the observations that we have been making about what's the implication of every iteration. So so at time t, let's define this ft to be the fractions, fraction of the weights of the experts that make mistakes. This is not counting the number of experts who made mistakes, but like just calculate the fraction of the weights of expert that made a made a mistake. Okay, and then using the same way of calculating the total weights after many iterations, we can write the total weight to be n multiplied with 1 minus epsilon of f1, 1 minus epsilon of f2, all the way to potentially the end of the time. So why is that the case? So notice that this is a randomized algorithm. So w t plus 1 is equal to let's calculate the two sides of the probability, since ft is a fraction of the weights. So with probability f with probability 1 minus ft, then this part of weights will remain what it is, and for the other half, it will be ft multiplied with wt, but then discounted by a factor of 1 minus epsilon. So if we consolidate everything together by combining the terms, then we get combining these two terms, and they sum up into wt, and then minus ft wt multiplied with epsilon. So this will be like 1 minus ft epsilon wt. Okay, and if we substitute all these into here, then we get this calculation of the total weights at every iteration. Okay. It doesn't really matter like how many iterations we do this. Okay. Now let's like take the logarithm on both sides. Okay. Get log w is equal to log n. Since we have a product, and the logarithmic transformation will make a product the summation. We'll have sum over t from 1 to end of the times. Let's call it capital T. Log 1 minus epsilon f t. Okay. So let's make use of the lemma that we've learned just now. So we know that log 1 minus x is smaller than I guess minus x. Okay, so by applying this, we get log n plus then we can get rid of these log factors and get something that's that clearly depends on minus epsilon sum of t f. But what is ft? Ft again is a fraction of the weights of the expert, and by the rules that we're choosing to predict according to these weights. So in other words, the sum over ft. So all these ft's is actually equal to the expected number of mistakes. So this is a randomized algorithm, but the expected number of mistakes, so this is random variable. When we take the expectation, it gives us back on the sum of ft's. Okay, so that is maybe let's modify the problem into using m to denote the number of mistakes. Okay, which says that you get log n minus epsilon m. Okay, this is a good sign because we have this epsilon of m on the right-hand side of the inequality, and if we toggle it to the other side, then we get an upper bound of m. Okay, but on the left-hand side, let's like before, let's work out the lower bound. Again, so W is the total weights, and we know that the expert, the best expert in the hindsight have made m mistakes. So using the same argument, if the best expert have made m mistakes, and the smallest weights that you would end up getting are 1 minus epsilon to the power of m, because in those cases where maybe like when the best expert makes a mistake, everybody else would have made a mistake, then this f1 to ft, in those cases when the best expert has made a mistake, might have the fraction that's approaching 1, right? So that's a valid lower bound. So we know that this is always smaller than W. Okay, so what that is saying is that notice that we have log W on the left hand side. What this is saying is that we have log of 1 minus epsilon to the power of m, smaller than minus epsilon of m. So again, do everyone follow like what this step is? Or why this step is the case? Okay, so let me maybe explain this a little bit more. So W is the total weights. Okay, so the total weights is smaller than the weights of the best expert. Okay, so the weight of the best expert is the weight H star. And the weight of H star is smaller than, since the H star only made m mistakes, so this is smaller, this is equal to 1 minus epsilon of f of this particular index, 1 minus epsilon f of this particular index, I1 to IM. Okay, so let's pick out all the indices where this H star has made a mistake. So notice that this W have a product that's as long as the entire sequence, but only in a subset of them, the weights of the best expert were discounted. Okay, and now we can lower bound this by choosing this fraction to be as large as possible. Let's choose it to be 1. Then we get 1 minus epsilon to the power of m. Okay, so I hope that that's clear. So now that we have this, let's get m log 1 minus epsilon smaller than log n minus epsilon of m, and that implies m is smaller than m times minus log 1 minus epsilon over epsilon plus log n over epsilon. Okay, so now the coefficient look like that. By applying this other lemma that we talked about in previously, 1 minus x is larger than minus x squared for all x in 0 to half. Right, then we can further upper bound this with m epsilon plus epsilon square over epsilon plus epsilon log log n. Okay, equals to 1 plus epsilon of m plus log n over epsilon. What does this tell us? This allows us to choose epsilon. As we choose epsilon to be close to close to 0, then we actually get something that depends logarithmically in n, and also it only adds a little bit to the regret, right? If we move m to the other side, we can bound the regret to be smaller than epsilon of m plus log n over epsilon. And if we choose if we choose choose epsilon optimally, then we will get if we choose epsilon optimally, then we'll get a regret that's proportional to log n. Okay, log n and square root of n. Okay. So far, we've talked about sequences of algorithms that allows us to learn from a bag of experts. So none of this is actually convex optimization problems. And we took a completely algorithmic route by trying to figure out the algorithm that minimizes the regret bound. And then in the agnostic case, we try to develop algorithm that minimizes regret. Okay, so this this approach of doing weighted majority voting can actually be generalized into the case of a loss minimization. Okay, so let's consider the slightly transformed setting where instead of having just the 0-1 prediction error, so let's say that each expert H incur loss of H at every location, at every time t. Okay, and then we want to define the regret So this is a slight generalization of the previous setting to be the cumulative regret that's obtained by your chosen expert minus the best expert in the hindsight at every location. Okay, so so this is called I guess hedge algorithm. The corresponding weighted majority rule that solves this problem is essentially the same as before, but allows for a more general loss function LT. Okay, so the hedge algorithm says that you pick expert H with probability proportional to the weights of this expert, divided by the total weights. So basically, you're doing the same randomized algorithm as a weighted majority votes, and then you incur loss of LT of HT. And then after that, you discount the weight by making it smaller by e to the power of minus L Ti. So notice that when we choose this loss to be either 0 or 1, then this e to the power of epsilon LT is equal to 1 if there isn't a mistake, and it is equal to e to the power of minus epsilon when there is a mistake. And this transforms into the previous 1 minus epsilon calculation as we had before. So this epsilon is different from the epsilon that we had in the previous slide, in the previous page of the derivation, but there's a one-to-one mapping between these two. Okay. For all H in the hypothesis. Okay. This is called the hedge algorithm. So the analysis of this is essentially identical to what we've seen previously. So so I'm leaving the analysis as an exercise. As the randomized weighted majority. So what I want to point out is that instead of having 0-1 loss, this actually allows us to formulate this as a solution to a so-called online convex optimization problem. So from the point of view of the optimization, so we want to solve the problem that minimizes the sum of some Fi theta with respect to some, like maybe a convex set, and this is a sequence of convex functions that we observe online in every iteration, and in the setting of learning from expert device with general loss, then this Fi is essentially is equal to the I guess the inner product of Xi transpose theta. Okay, and Xi is equal to the loss of the first expert, the loss of the first expert on this problem, loss of the second expert on this problem, and loss of the last expert on this problem. Inner product with the theta is our probability of picking each expert. Okay, so theta is a probability distribution. So the probability of H given the input, given the input index, right? So all we have is an index here. Okay, and this convex set is a probability simplex. Okay, so you can view this problem of learning from expert advice, even though it is not a convex optimization problem, you can view it as a convex optimization problem with linear sequences of reward, of linear sequences of loss, and then you want to minimize the loss without knowing what you're optimizing, and you have to you have to try to come up with a sequence of probability distributions to sample from these experts online. Okay, and maybe like with this view, we can talk about the more general picture. So what if Fi is convex rather than linear? Can we solve this problem equally well? What if this F is convex and smooth? What if this F, the sequence of the F satisfying is convex, smooth, and maybe strongly convex? Can we improve the regret bound? And maybe suppose we change this setup. So instead of having a probability simplex, what if it is just an affine constraints? So what if this is a general convex set? Specifically, suppose these theta are norms. They are defined by norms. Maybe a second order cone. Or other cone, other conic constraints. Or maybe this theta is semi-definite cones. And what can we say about this online learning problem? So so the solution to these questions is in our textbook by Elad Hazan called Online Convex Optimization. It starts from the idea of marrying the first order optimization and convex optimization in general with a problem of learning in the adversarial environment. Marrying online learning with So the example that I gave you is a good illustration of what online learning can do. That sometimes seem pretty remarkable in the sense that you are making a very weak assumption about how the world works. You're not assuming that the features are drawn from certain distribution. You are not assuming that labels are created through some labeling process, through the generalized linear model, through the Bernoulli distribution or anything. You're essentially not making any assumptions. And the sequences of observations can be chosen by an adversary who deliberately tries to beat you. And it can even be adaptive in the sense that if you choose to do something now, and the adversary may decide to modify the labeling process after you have taken your choice. It can be fully it can even be fully adversarial, and the expert might have information that's independent that depends on your choice. If you choose to predict up, then the expert would say that, well, let's let the outcome be down. If you choose to be down, the expert may say that, well, let the outcome be up. So the expert may decide to change the outcome related to what you would end up choosing. Okay, so even in that situation of extremely adaptive adversary, then online learning still have a place to be, and we can derive regret bound that grows sublinearly in the horizon of playing this game. Okay, so in the next lectures onwards, so we'll start talking about these questions, and you'll see that a lot of the techniques that we'll be using are coming directly from the foundations that we've already laid down on convex optimization, and we'll see how we can generalize the learning from expert device today to more general cases, and we'll even talk about the second order approaches called online Newton's updates that allows us to achieve significantly lower regret on the a larger family of problems. Okay, so with that, I'll end the lecture today, and we'll resume on Wednesday. The homework is due on Wednesday, so please try to finish it on time. So we do have a very lenient policy on late homework submissions. So if you really cannot make it, use your budget for late days, and even if your late days used up, you may still get a fraction of the credits for the homework. So do try to finish the homeworks, because it's a big part of the training. Do try to finish the homework even if you can't catch the deadline. Okay. With that, I'm happy to answer any questions, and if not, I'll just see you on Wednesday.
Can I ask a question about the homework?
Yes, please.
So I am doing homework 3 question 1B part, and the part 3 is to derive the dual of the 2 mean cuts problem. Mm-hmm. I know it's supposed to be a max flow, but I am unable to get to the end. So I can show you my progress. Basically, I'm a little bit uncertain about how to deal with all the axes.
It'll be difficult for me to help you, like if you just tell me verbally, like
yeah, I can show my progress.
Like why don't you post on Piazza your progress with a like private question, and then my TA or myself will find time to help you.
Okay.
Okay.
Yeah.
If not, like maybe the first question is probably like an easier thing to do, like if you are really stuck with that part.
Yeah. So I also have a quick question about question 4 part B.
Mm-hmm.
What I get is there is a negative sign in front of the x, like minimize something and subject to this thing is greater than 0. I mean, like that to 0, right? But I have a negative sign in front of 1 over 2x.
Yeah, take a look at the short complement and compare both constraints and see what their differences are.
Okay, so you're saying they might just be the same?
Yeah, take a look at short complement, and there's a good coverage of that in the Boyd and Vandenberger book.
All right, thanks.
Actually, for this question, I think many students are having the same problem. Can we post it on the Piazza?
Yeah. I think so. I think that's a good idea.
Okay, I will do that.
Hi, Professor. I have a question with regard to the bound 2.4.
Mm-hmm.
Should it be 3.4? 3 point something?
Wait. So you're talking about you're talking about the weighted majority, right?
Yes. I can't. It's like log 2 over log 4 over 3. That one. Kind of forgot which. Yeah. So log 2 over log 4 over 3, it is 2.4. But on the coefficient of the log n, it's 1 over log 4 over 3, right? That one is 3.47 something.
So I'm taking the larger of the two coefficients.
The larger should be.
Yeah. So you can, I guess, alternatively take a base 2 log. Right, if you take base 2 logs, and log 2 would be 1, and then you're left with 1 over log 4 over 3, which is right. So log 2, 4 was 4 over 3 is like 0.4, something like 1 over log 2, 4 over 3 is 2.49. Yeah, so it's actually 2.41, right, rather than 2.4.
Yeah. So, okay, I got it. So if you take log the base is 10, then or the e will be different answer, right?
Right. So yeah. So the point is that there's a constant in front of m. So like and we've also we've also done a similar calculation more generally when we have those epsilons, right? So when you have those epsilons, you can play with this epsilon. I think, like, depending on what log base of logs that you use, you should get the same answer, because this is a change of basis formula, right?
Then it won't it will be a little bit different, but you have to change the log of n as well. Like the log of n will take based on 2 as well.
Yeah. I guess we're not worrying about log of n yet. That's right. So the log of n will be slightly different, but the coefficient in front of m should be always 1 over log base 2, 4 over 3 due to the change of basis.
Yeah. Gotcha. And another thing is about the regret, right? We can get a regret, kind of negative regret, right?
Oh yeah. That's a good point. So so the regret can potentially be negative, but that doesn't affect the upper bound, right? So the regret is a worst case bound. It says that in the worst, if the adversary chooses the worst sequence, and you still satisfy this performance guarantee. But in cases when it is much easier to minimize the regret, so you can potentially have a non-stationary policy that achieves a better regret compared to the best single fixed expert in the hindsight, right? Since you are allowed to change your prediction at every iteration. So if it is a piecewise constant style ground truth, then you might be able to do better. So for more information on that, check on the paper that my student Diraj have recently wrote. So that have talks about the so-called dynamic regret, which compares to the point-wise optimal expert in the hindsight, which is optimal for every iteration.
Gotcha. Thank you.
Yeah, good questions.
I ask another question about homework.
All right.
Question 4 and C part. To show the optimum values are equal and both can be attained, are we supposed to show the strong duality of the SDPs? So
yeah, so that would be an approach.
That would be an approach. So that means we should show that both the dual and primal are strictly feasible.
Yeah, just construct a point and then use Slater's condition.
Okay.
Yeah, it should be pretty straightforward.
Okay, is there a different approach?
Well, there are more general conditions than Slater's condition, but for the interest of this question, Slater's condition suffices.
Okay. Thanks.
All right. Thank you all. Guess I'll see you guys on Wednesday.